Hello, everyone. Thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on Guide to Using Simulations for HIRF Certification Activities. Before we start the presentation, let's review the user interface. The large window in the upper left is the primary window for today's webinar. You should be seeing the title slide right now. To the right of that, you'll find the Q&A window. If you click the arrow next to Q&A, you will see a field at the bottom of the screen where you can submit questions. At any time during the presentation, you can submit your question. Your question will be placed in the queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. Okay, on to today's speaker. Cody Weber is a principal scientist and co-owner of Electromagnetic Applications, where he has been using computational electromagnetic simulations to support design and certification activities across a wide range of commercial, military, and space platforms. He has focused his analysis on lightning, HIRF, EMI, EMC, and P-static evaluations that are required areas for electromagnetic effects compliance demonstration. He has been involved and led many validation efforts to characterize the relationship between simulation and test results. These efforts are an essential part of the certification process dedicated to understanding the aircraft response to electromagnetic environments. Now, without further delay, I'll pass it off to Cody to get us started.
Thank you very much for the introduction, Kaylin, and thank you to all the attendees who are joining this webinar. For the webinar today, I'll give a very brief introduction to EMA as a company, and then I want to spend a little bit of time reviewing the HIRF certification activities and reviewing some of the guidance material provided for those. And then I'll get into some of the details, which will be the bulk of this presentation, which are simulations. Similar to what is shown here on the title slide. So EMA, as we're better known as, is Electromagnetic Applications. We have headquarters located in Denver, Colorado. Actually, we're in a suburb just to the west of Denver, which is Lakewood, Colorado. And there's a nice view of the mountains from my office here. We have some employees scattered around the United States, and we also have an office in Pittsfield, Massachusetts, where our space radiation effects chamber is being built. We have a European office, the southwest side of Paris, and we are a small business with about 35 employees, but we're growing because there's lots of need for the type of work that we do. And what we do here at EMA is primarily expertise in electromagnetics, and we have a commercially available simulation software that I'll be talking a bit about today called EMA3D Cable. We use that in support of analysis for aircraft in different electromagnetic environments. And anytime you're getting involved with the electromagnetic environments on aircraft, it all ties back to design and certification support. And so over the years, we have developed a consultancy being able to help customers understand how their aircraft should be analyzed for the different electromagnetic environments, and then also being able to use our simulation tools to support those activities. And anytime you're doing analysis or assessment of the environments for aircraft, there's a testing aspect to it, being able to anchor it, your analysis and understanding to the real world. And so certainly we have experience in understanding the tests that are employed for these activities and being able to validate our simulations to the testing. And so we're talking about HIRF today, but the type of electromagnetic environments we also support are lightning, both from a direct and indirect effect standpoint, P-static, EMI, EMC, and that refers to crosstalk between cables, as well as all of the radiated or conducted assemblies you have to consider. EMP, both HEMP and SGEMP. RFI, we have a team here dedicated to doing co-site radio frequency interference characterization with your antennas and your platform. And then we also have a growing team of spacecraft charging analysis. We have a software that we use for that to evaluate charging effects on dielectrics in space environments. And as I mentioned, we also have a radiation effects laboratory that we're building out in Pittsfield, Massachusetts. So that's just a brief introduction to who we are as a company. So now I'll talk a little bit about HIRF certification. And there's a couple of documents that are important when considering HIRF certification activities. First one being AC20-158. And so just a quick background on HIRF. HIRF is high intensity radiated fields. And these are emitted by transmitters and antennas from land, air, sea, or space And it's for the environment definition, it's a plane wave with frequencies ranging from 10 kilohertz to 40 gigahertz. And as you look through the guidance material and you do your evaluations, you may only be required to go up to 18 gigahertz, but then that higher frequency range, what you have to do for evaluation depends on the operational frequencies associated with your aircraft. And so if you have certain antenna or systems operating at the higher frequencies, you'll have to do some evaluation there as well. Whereas lightning is a natural environment, HIRF is a man-made environment. The antennas and transmitters are built for communication and other purposes, and aircraft, of course, have to operate in environments when they are exposed to those electromagnetic fields. And whereas lightning can be a physical damage or a system upset type of environment, HIRF is just a system upset environment. There's not physical damage that occurs from the HIRF threat. It's the coupling to your sensitive electronics equipment and disruption that occurs from that coupling. And so with that in mind, there's two types of environmental conditions that are necessary for HIRF threat to be realized. One of them is the power associated with the transmitters, that you need a high power RF transmitter or high gain antennas, and then proximity, that your aircraft has to be flying close by to those transmitting antennas. And here's some examples of the type of transmitters we're talking about that produce the threats. And there's many more than what is listed here. Okay, so for HIRF regulations, depending on if you have Part 23, 25, 27, or 29 aircraft, or even a VTOL aircraft, there's a certain regulation in that you must comply with for HIRF certification. There's been some rewrite of the Part 23 with Amendment 5 and some of the SC VTOL stuff. So some of those numbers have changed from what they were listed in AC20-158, but it's a similar approach to the outline that is there. And so, as I mentioned, we'll start with AC20-158, and then we'll talk a bit about the ARP5583. And I'm not going to go into the other documents listed there, but certainly the DL160 testing of Section 20 could be appropriate for what you have to do verification-wise. But I'm not going to dive into that today. So why is it important to consider HIRF? Well, there's a nice sort of outline description in the AC that talks about this. And for purposes of aircraft protection, you have to make sure that your aircraft electrical systems can operate effectively and safely. And then over the years, as we get more advanced in our technologies, and we have an expanded frequency range, and we have new and novel materials concerning composites, glass fiber, epoxies, other radome materials, that it sort of changes the coupling response of the aircraft as to what may be considered more traditional metallic aircraft. And so it's certainly a focus of authorities and an emphasis on safety for aircraft to be able to certify to the HIRF environment. There are 5 general steps that are outlined in the AC, and at a very top level, you have to identify the systems that require HIRF assessment. You have to be able to establish the external HIRF environment appropriate for your aircraft. You have to be able to establish the test environments for verification purposes on your installed systems. And I've highlighted that one because that is the area that I'm going to focus on today, being able to establish that test environment. And then, of course, there's the verification and compliance activities associated with steps 4 and 5. So an important thing to understand, and I'm sure many of you that are attending this webinar are uncomfortably familiar with the aspects of HIRF certification. And it's there can be a lot of steps involved, and they can be very detailed. But at the end of the day, what you're trying to focus on here is functionality of your systems, that you will categorize your systems based on functionality and be able to demonstrate that the function is maintained adequately through the operation and exposure to HIRF environments. And associated with that, there's a categorization of your equipment or systems in terms of catastrophic, hazardous, and major failure conditions. And so that gives you the level A, level B, level C classification that is commonly known for HIRF certification purposes. And I'm not going to talk about how you go into doing that. That's its own area, and that's not the focus of this presentation here. So for the external HIRF environment, the step 2, there's the tables that are provided in the AC. There's HIRF environment 1, 2, and 3, that for different frequency bands, there are field strengths that are considered for that particular HIRF environment. These are expressed in field strengths in terms of RMS. And so if you're wondering what those environments are, there's in the AC, I believe I can't remember if it's 5583 or AC158. The fixed wing severe environment that's listed, which sort of encompasses a worst case estimate of the electromagnetic field strengths in the airspace, but it's not typically used for HIRF regulations. The ones that are is the certification HIRF environment 1. And so this is the estimated electromagnetic field strengths encountered in routine airplane flight operations. Environment 2, and so this is on or about the airport in which routine departure and arrival operations take place. And then there's the rotorcraft severe, so that aircraft that can hover or have flight paths, hovering more around the airfield, have a bit more severe environment. And so then these are the 3 different HIRF environments that you may have to consider for your verification purposes. And so while you do have those different operational environments, you have to do an evaluation of the HIRF coupling that occurs to your aircraft. And then when they say established test environments, and this is what I'm talking about, is the coupling that happens from your free field plane wave excitation of your aircraft, the attenuation of fields in the different cavities of your aircraft, and the coupling to the cables. And so in general, the HIRF environment will either penetrate through the apertures or couple an antenna-like response to your aircraft to establish an internal RF environment. And certainly the electronic systems will be exposed, and the fields will couple to those cables or to those equipment directly. And then the internal environment that you have to characterize is affected by the apertures. So the main windshield in the cockpit, the cabin windows in your fuselage, any of the connectivity between your bulkheads, your floor, and the surrounding structure creates seams in which currents flow across and a voltage develops, and it creates an internal field for that particular cavity. And so these are all things that they may not have to be assessed directly, but they all impact the coupling response of your aircraft. And the focus today for me will be on the level A systems, because that has sort of the most stringent level of understanding associated with your HIRF environment for your aircraft. And so when you're considering this, as I say, it is zone specific, such that if you have a cockpit area with a windshield aperture, you may have a floor and a bulkhead at the back that somewhat separates the zone of your cockpit from the other areas of your aircraft. The same can be true for different avionics bays, whether it's your forward avionics bay, a mid, or an aft. There could be structural design associated with your aircraft that sort of separates that zone from other zones of your airplane. And so essentially what you have to do is go in and understand for your specific zones what attenuation is provided by the design of your aircraft. And then this is typically done through testing, analysis, or similarity. And so some of what we'll be talking about today is using analysis to establish these environments in your aircraft. So, of course, there's other activities associated with the compliance demonstration, that you have level A displays, level B and C, but the way that you would characterize your test environments is not done the same way for those level B, level C, and display systems. There's some generic transfer functions that you can use for your level A displays, and then there may be some lookups that are available rather than a full aircraft assessment necessary for level B and C classification. And then, of course, you have to do your compliance verification activities, which is your, if you're not doing a full threat aircraft analysis, this is doing your subsystem verification and some equipment verification as well. And I'm not going to go into all the details of the equipment verification. Like I said, I'm focusing on the environment specification for your aircraft. So there's the nice flow chart that's presented within the AC, talking about as you go through and assess your systems, how you would go through an aircraft level verification and system level verification. And so if we're looking at figure 1 on the left, there are the sort of parallel paths. And I've seen different programs approach these differently, such that, Sometimes they do it in parallel where you're doing your system level verification with what you believe to be your aircraft environments, and then doing a test to verify that your equipment level verifications were done at environments that encompass the environments you would see on your aircraft. And then sometimes I see it that you set your aircraft levels first before you go to your system level verification. So there's some leeway in how you approach that. And what they've really tried to outline in this flow chart is that it's somewhat done in parallel. It's kind of separate considerations for that. So if we're talking about the aircraft environment or the aircraft level verification, the step that I'm going to focus on in this chart is step 10. And so it's circled in red, and it's the aircraft low-level coupling tests, which in my experience are perhaps the most common aspect for understanding the environmental response to your aircraft to the HIRF environment. And so there's a subsection breakout of that step 10, which is shown on the right in figure 2, and that there's a few different ways to characterize the responses of your aircraft. One of them is through a low-level direct drive test, and this is dedicated towards understanding the current response on your cables. There's the LLSC, the low-level swept current test. Again, this is dedicated to understanding the current response on your cables. And then there's a low-level swept field test, and the LLSF. And so the LLSF is sort of an attenuation response of your aircraft in the different zones. And the LLSC is what couples to your cables. And certainly you have to consider, as they route through different regions, the different types of coupling that may occur to them. And so the breakout of step 10 is shown here in figure 2. And really what I'm going to talk about today is these three different types of aircraft characterization. So your low-level direct drive, your low-level swept current, and your low-level swept fields that you would typically analyze or characterize as part of your HIRF aircraft response. So within the level A systems, there's this other sequence of steps that are typically followed for certification. And the first few are dedicated to doing the equipment verification or system verification, and that's the equipment test, integrated system tests. And of course, those are very important to understand. But what I'm going to focus on again is the aircraft level. And so starting at about step 7, that you have to do some assessment of your aircraft, and you have to decide how you will do that assessment. And there's the option to do a high-level test. There's certainly some tricks and complications associated with doing a full HIRF environment test on an aircraft, because the aircraft must be powered on and operational to do that. It's kind of nice in the sense that if you're able to do that, you can cover all of your verifications in one fell swoop and not have to do the subsystem testing. But certainly there are complications involved. And when you do the high-level testing, you're really not developing a detailed understanding of how the HIRF interacts with your airplane. You're just demonstrating that your systems operate through that environment. So really, in my opinion, the more thorough way to analyze and understand how HIRF interacts with your aircraft is to go through the low-level coupling tests, and it's with those three different categories that I talked about before. And so really the remaining focus of this presentation is on those low-level coupling. Okay, I'm going to talk a little bit about ARP5583. So once that you have set your path for doing aircraft level verification, there's many details in ARP5583. And so for LLSF, this is attenuation measurements in your aircraft zones, typically in the range of 100 megahertz to 18 gigahertz. As I say, you may have to go up to 40 gigahertz depending on the operational frequencies of your aircraft. And you'll also have to do characterization of your bundle currents on your harnesses from 10 kilohertz to 400 megahertz. And so this is typically done that you apply an environment to your aircraft at a low level, and you get a measurement, and then use a transfer function combined with the HIRF environments listed before, 1, 2, or 3, and then that information is used to specify your aircraft environment for certification purposes. Okay, so I have a few slides here that are quite lengthy in text, but in my opinion, it's very important, and not everybody knows about these sections. And so there's some really good words in the ARP5583 document talking about analysis. And I'll just read this, and there's a couple more on the next page that really help to support the idea that I'm promoting here. This one here is talking about if you're using analysis to determine aircraft attenuation and transfer function characteristics, the test data Test data should be provided to support this analysis. Any analysis results should take into account the quality and accuracy of the analysis. Significant testing, including aircraft level testing, is required to support. So this is the idea that you have to do validation somehow to anchor these analysis or simulation results that you have. My argument is that the most accurate results for your environmental response will be obtained through some combination of test and simulations, and that simulations can reproduce the test results very well, and that what you'll be able to show eventually is that you do not have to do as much testing, or you could even eliminate portions of your lengthy test campaigns by supplementing it with analysis. And that's the sort of the overall approach that I'm promoting. And additionally, that if you have a validated model, that you will be able to use your simulations that have been validated on previous test campaigns, that you can use this technique, this analysis technique, to do variations or permutations in your aircraft design and certify your variants without the need for those full aircraft tests in future applications. I just want to quickly highlight that, I really like Section 4 of ARP5583 that talks about practical design considerations. There's some good information in Section 4.1 talking about coupling mechanisms and then different grounding, bonding, shielding effects for consideration of design and how they impact your electromagnetic protection. But the area I want to talk about more is the Section 4.4 on analytical methods. And that there's just some quotes here that really highlight my beliefs about analysis and how it should be used in these programs and assessments. And so I'm just going to read this small section here. The testing of a complete aircraft containing complex flight safety electronics in various HIRF environments can be time-consuming. An aircraft trial carried out over many weeks is likely to investigate only a small number of possible combinations of system modes, HIRF illumination angles, and frequencies. It is unusual for a complete aircraft to be made available for many weeks of ground testing prior to production certification. A more complete assessment can be accomplished using analysis of HIRF hazards. An analytical approach can mitigate undesirable impacts on the aircraft certification program. And so, it can also be used to help define and select test methodologies, and then also assess completeness and validity of the test results. But the idea that in general, airworthiness certification should be achieved through a combination of test and analysis is something that I believe strongly. And it's words that are listed directly in that guidance document. Okay, there are a few more here, and then I encourage you to read this on your own, but for the sake of time, I'm going to skip through this. I will highlight the bottom one there, that in general, errors in analysis are comparable to test errors in size, and that if you have efficient design processes offloaded from expensive testing to less expensive analysis, this is beneficial. And this process identifies potential design weaknesses earlier in the development process. And that's a key point here, that what you are able to do with simulation can be done earlier in your design and development process than what you can do with full aircraft testing. And that is one of the huge benefits associated with doing these types of analysis. Okay, last point here with the lengthy text, I believe, is associated with margins, because anytime you do numerical analysis, there's a margin conversation that comes up. I particularly like the margin assessment that is used in AC20-158. It says that margins are not required if your HIRF compliance is based on tests or specific aircraft model and system undergoing certification. Margins are also not required if your HIRF compliance is based on analysis or similarity if the process validation is robust and the data is well substantiated. And then so I think that is an important distinction that is made in this document here, and that really it lends some confidence to the analytical techniques that what I'll show here a little bit later are some of the ways that we can sort of develop a robust substantiation, but it is certainly capable with the tools and understanding we have with aircraft response to be able to develop that robust substantiation with analytical techniques. Okay. The last bit on the certification side is an analysis plan. That if you're going to be implementing simulations or analysis, it's important to establish a plan. And that some of the details listed here are things for consideration, and being able to communicate that effectively with your authorities is an important part of the process as well. Okay, on to EMA3D Cable, which is the simulation tool that we use for this analysis. So kind of I've been hinting at this up to this point with quotes and identification in the guidance documents, but I'll flatly state it here. There are two primary reasons that we would use computational electromagnetic simulations. One is to support design, so that if you can do during the build or design process a justification for a design that you're currently considering, or an evaluation if additional protection is needed. These are aspects in the parameterization or components of your model that you can adjust to match your design elements and do that evaluation. And this can be done earlier in the process than anything can be done by testing. And there can be a large cost and schedule savings associated with these activities. And the second one is on the certification support side. And there really is a growing acceptance within the authorities about using simulations for certification. And what we've been able to show with work that we've done in the past is that you can establish aircraft electromagnetic response very accurately, and that these results can be helped to reduce program testing or to help guide test inputs. And that there's both of these stages, design and certification support, can provide significant program cost and informational benefits. And just evidence that there's a growing acceptance of these techniques is that within the AE2 Lightning Committee that I participate in, there's going to be a new document coming out in the next few years dedicated to simulation for certification purposes. And it's not clear what the full scope of that document will be. Right now it's targeting lightning effects, but certainly there is a growing need and use for HIRF applications as well. And whether or not it's in that document or a separate one, certainly HIRF will be a part of that assessment. So the cable, the tool that we use for these simulations is EMA3D Cable. It's well suited for these types of analyses, especially up to 400 megahertz. We have found techniques that are applicable to go to the higher frequencies if we use submodels with smaller mesh size. And the same model that I'm showing today that we use for HIRF assessment can also be used for lightning, indirect effects assessment, EMP analysis, EMC characterizations, or P-static simulations. And that it's really, the power of the simulation tools goes well beyond what is capable in test applications. So here's a snapshot of what the tool looks like. It's EMA3D Cable. It is distributed by ANSYS, and it's a commercially available finite difference time domain solver. And we have a 3D plane wave or a full wave solver tool algorithm. And we also have a complex transmission line harness solver. And so we have these two tools integrated together for co-simulation purposes. So when you're developing your simulation models, there's varying complexities that you can add to it. There's a lot going on in this chart here, but just from a high standpoint, you can understand that there's early stage models that you can put together very quickly that have some of the exterior structure details and maybe a few interior structure details and maybe a couple of harnesses that you can really start to understand at a very fast and high level the types of couplings that may occur for your aircraft, which is some simple specifications of your structural materials and some of the routing and system implementation details that you have. And really, this is the best place to start to develop confidence in the numerical technique as it applies to your particular aircraft and to get some actionable results early in the program. Then as you go forward in your development and your design, then they can sort of convert to more high fidelity models, ones that would be appropriate for your full environment specification. Here at HIRF, we're talking about LLSF and LLSC, and those are the high fidelity models I'm talking about that can be used for certification support. So the different environments we're talking about are LLDD, LLSC, and LLSF. Try to say those 3 times fast. So for low-level direct drive, this is where you do a current injection onto your aircraft. It's somewhat similar to pulses that you might inject for lightning characterization, and sometimes I've seen these tagged on to the end of lightning testing that you might do for indirect effects ATL assessment. And what you can do is measure currents on the exterior surfaces of your aircraft. And when I say currents, it's usually done as a magnetic field or a B-dot sensor. And what you would use is a transfer function and a 3D simulation model to show what your free field impingement current density on your aircraft skin is captured as from your simulation and as compared to what you get during testing, and to make a transfer function out of those results so that you can use your measured LLDD currents from testing and this transfer function to convert it to the HIRF environment. And this process is described within 5583, and it distinctly mentions that using simulation or 3D analysis is an integral part if you're doing this analysis. The other type of characterization is LLSC, and so rather than doing a direct drive onto your aircraft with a transfer function, you're using an antenna to illuminate an electromagnetic wave onto your aircraft and then measuring the bundle current at certain box locations. Typically, it's done at 50 millimeters from the box connections. Always when using your results from these analysis, there's some post-processing that must occur. And, it can involve enveloping or averaging, some other post-processing techniques I'll get to in a minute. But that's an important part of the process as well. And what we found and what we have seen over the years is that simulation can replicate quite well what is done during testing. There are some very key aspects to doing the simulation that I'll talk about shortly, but it certainly can be done. And as I've mentioned before, one of the great benefits of the simulation is that you can expand upon the testing that is done, both for illumination angles and for the amount of probe positioning and outputs you can generate, as well as any variations that you might want to implement into your aircraft design. So talking about cables, we have done a lot of this analysis over the years, and we have been able to use our simulation models to investigate what parameters of cable harness details are necessary to get answers that match testing. Because at the end of the day, it all ties back to the validation purposes. If you're going to convince the authorities or anybody else that anything from your simulations are worth a damn. So what you really have to do is go in and resolve the details of the harness in a complex branching manner and with accurate resistances. I know there's a lot of information here, and you guys can read about it on your own after the fact if you like. But some of those details are related to the resistances, the routing, and the branching. And as you change these parameters within your model, this is one of those more simplistic models that can be put together quickly to do these kinds of evaluations. You can start to understand what kind of effect the different parameters have on the coupling response. That as you change the resistance of your cables, and this may be from overbraid shielding types as you go from more traditional nickel copper to maybe perhaps the more resistive armor light or amber strand mixes that are available today, you can get a good idea for what that coupling response might be like on your aircraft. And with those details associated with the cable harnesses, there's really a lot of the transfer impedance details that can be implemented with our tools. And you can use it in terms of a specification where you enter the parameters directly, or we have a algorithm that could calculate based on the carriers and the strands and the weave angle associated with your braids, what that transfer impedance might be, if you have no idea and there's no transfer impedance measurements available. So when you get your LLSC data, one of the benefits from the simulation is that you can do the multiple cases, and you can take all your incident angles, you can take all your measurements for your particular box, and you can do your worst case overlay. There are some good examples in the ARP that describe this, but basically when you have multiple together and you sort of plot them on top of each other, you see what the worst case results are for that particular area that you're looking at. And then you can do your enveloping associated with that worst case overlay. And it's a very good argument, in my opinion, that you're capturing the reasonably severe environment associated with that particular region. And of course, there's the 20 dB per decade fall off that they attribute with the LLDD and that is commonly used at the lower frequencies. So when it comes to LLSF, these ones are a bit trickier to characterize and validate, in my opinion. And that as with the cable currents, these simulations can replicate and expand upon what is done during testing. But there are some tricks if you're going to be doing a validation or as you process your data to use for verification purposes. That when they do these measurements, oftentimes they're done with antennas that are the horn-shaped antennas, and that what these do is sort of a averaging of the fields over a spatial region. And that, so what we do in our analysis is we try to replicate that, and we don't put the probe in directly, but we will use what we call a boxed region probe, where we can set a specific spatial region in our model that replicates the horn receiver positioning in a test, and those can be somewhat equivalent. So that what you do is you probe multiple fields within that boxed region. And what we can understand as that result is that there's a minimum, a maximum, and an average field that can be computed for that region. And that's the plot I have shown here on the lower right. And so that if you just pick a single cell within your finite difference model and you use that for your field value, you could be high or low compared to testing, depending on where you fall in that min-max range, and that you can have quite a bit of variance associated with it. And that so the spatial averaging associated with the testing is important to consider when you're doing this field capture in your simulation models. And so it may be appropriate to do all of your plots in this nature where you're showing a min-max and an average. And then really what we find to be the best is using that average value for your comparison to testing. And then another key point is that there is a 5% bandwidth averaging that is typically done for the test results. And you can see on the top plot that the raw result for LLSF attenuation has a lot of fuzz and spikes associated with it. And then when you do the 5% bandwidth averaging, it sort of smooths it out. And so in the terms that we have here with our simulation results, we use the term smooth, but that means the 5% bandwidth averaging. And you can see that for some of the points, like in this region here for a few hundred kilohertz, that the real response is around below 15 dB attenuation. But if you consider the 5% bandwidth value, then it's above 25 dB. So it's a 10 dB difference there. So that if you are just getting a raw field value from your simulation and trying to compare it to testing, you could be off by quite a bit there as well. And so implementing these regional spatial averaging and the 5% bandwidth averaging really improves the quality of correlation between the simulation and the testing, has been our experience. And so we have this implemented as a standard probe within our EMA3D Cable tool to be able to do this box region probe. Okay, and then finally, the absorption losses associated with cavities. Again, this is something that's very amenable to simulation, to be able to change these parameters, so that if you have a simplistic model here and you're changing the conductivities associated with the inside wall, the floor, and the window, you can really see the difference in coupling associated with those. And these were here comparing to measurements in this case, so that if the resonance of a cavity, a Q value, was determined for a few different cases, the blue chart here is simulation and the black is measured data, that as you start to modify these parameters, you really can get response that match what is done in testing. And so this can help give some insight as to the important or critical parameters associated with your simulations. Okay, so this is, I'm going to look at, we have a sample model here that we have recently developed in our EMA3D Cable tool. And when I say we, it was prepared, and both the model, the analysis, the simulations, and the data plotting by my colleague Megan McGuire. So here is the aircraft model. And so this is sort of a demonstration of how we might build this is a crude model in a sense. It's mostly an OML with some boxes and cables routed in it. And we'll look at how we can use this model to develop some of those LLSF, LLSC results. And for this analysis, we're using a broadband Gaussian pulse, shown there on the right. And we're using parallel computations, 50 cores for this particular analysis. And with those stats that we have, it's about 3 hours to do one of these simulations. Now, you'll see some of the results. We have the ability to go lower in frequency, and to do that, you just have to run it out longer in time. But for the purposes of this demo, we didn't do that. So what we have looked at here are two different plane wave orientations and incidence angles. And so basically what we did was a broadside illumination with the electric field oriented along the aircraft. And that's kind of what's shown there in the lower grid here. This is our incidence angle, our incidence vector, and our electric field orientation. And we also did one that was nose on towards the cockpit area. And so what Megan did for this model was she put in some sample harnesses. As everybody knows, the complex configuration of harnesses can be overwhelming. And so when we're doing this demonstration, we wanted to show something that was reasonable and actionable for people to understand. And so we just put in a handful of TSPs, and we did different branching configurations associated with them. And as I mentioned before, there's different harness shield capabilities within our tool, such that for any overbraid that you might have, you can implement those details in terms of specifying the carrier strands and weave angle, or using measured transfer impedance data as your characterization for those shields. So here's some examples just as the cables are routed through the aircraft, what the packing looks like. And I just wanted to pull for a second here what the tool looks like. And so that as you have this tool within your interface here, you can go in and you can visualize on these cables what the packing looks like. And we have lots of capability for adjusting this packing if that's something you're inclined to do. I have done some studies in the past, and as you rotate and move the cables around within the packing, that can help to disrupt the modes and resonances associated with cables. So depending on what your primary coupling mechanism is to your cables, and exploring some of the twisting or different configurations could be helpful. But it's really nifty that you can adjust these packings and they can be represented within the model in a complex way. And that for some of the ribbon cable analysis, if you need to do that, you can adjust that packing as well. And there's just a lot of capability for representing harnesses and geometry within our tool. Okay, I'm going to jump back to the presentation now. So, of course, it's helpful to do visualizations so that if you have your plane wave illuminating your aircraft, you can see it propagating. And these are two different cases. The one on the left-hand side is the nose incident propagation, and you can see what we're looking at here are surface currents. As the wave propagates along the aircraft, you see the wave front, and then you see reflections, and you see different oscillations that occur. And then the one on the right-hand side is the broadside. So you see the wing light up first and then transfer across, and then you see some of the resonances and skin current distributions that occur associated with that plane wave. We can also do field evaluations inside of cavities. So what we have here is a slice straight through the middle of the aircraft. And for the nose incident plane wave, you can see it light up in the cockpit region. And then what we have in our simplistic model here is a floor that separates the upper fuselage cabin from the lower. And you can kind of see the lower cavities that we have. The lower left-hand side is sort of a forward avionics region. And then there's a bulkhead before you get to the wing. So you can sort of see that front lower area light up first before some of the ones in the aft portion. And really, it can be insightful for the in your analysis to do this evaluation, such that if you're looking at the fields and the resonances that might occur within your different cavities, do you have leakage appropriately captured from one region to the next? If you have a completely enclosed, shielded region for one of your avionics bays with a lot of metal panels that surround it, you had better see some very quiet environments in that area as compared to the other higher exposed areas. And so those are things that intuitively you can use these animations to help your understanding. Now, if you're going to use the actual levels that are developed for verification purposes, you have to use the other probes. But these visualization tools are very beneficial when doing your assessment of your aircraft. Okay, so for the LLSC, the currents, we put in bulk current probes on our cables, and you see those responses pop up here. So this is just 3 examples in the sort of forward lower avionics region where we're looking at the coupled response to those cables. And in each of these, you see the aircraft resonance pop up around 4 megahertz. So you must consider for this one, it's a free space response, so it's a lambda/2 response that shows up here. Whereas if you did a low-level direct drive and you had a return array during testing, it might be a lambda/4 response. But for the dimensions of this aircraft, that is their appropriate response. Now we could have finer resolution at those lower frequencies if we went out longer in time with our simulation, but that wasn't necessary to demonstrate what is capable here for this particular simulation. So this is what it looks like. And what I've been mentioning before, and I'll emphasize again, is that one of the big strengths of simulation is its ability to probe many different locations. So you can expand upon what is done during testing. And so you have the ability to capture a lot of different cable currents at one time. This is the LLSF, so that if we have our boxed regions in the different avionics bays, we have one up by the displays in the cockpit, one in the lower forward avionics region, mid avionics region, or aft region. We can do our field characterization in those locations. And what we have shown here is the raw data and then also the smooth data. And so these are the average values. So as I talked about before, it's important to do the spatial consideration. If you're using just a single point, you're liable to get a max or a min. It could be representative of the average, but if you're trying to compare to testing, it's important to do that sort of average spatial box probe that we use here. And just as it is done for the cables, a lot of probes can be added here. And whereas you might only look at a few locations for your receiver positioning during testing, you really have the capability to expand upon that in the simulation. So you can look at a lot more areas, add a lot more probes, and be confident that the fields you're capturing are most reasonably as severe for your verification purposes. And that's a term that I'm trying to use more and more, is that when you do this characterization, you don't want to be so severe that it's not reasonable for verification purposes, but you want to be able to project confidence that you are capturing the most severe response in a particular area. And so, as I mentioned before and just talked about, you got to really look at that spatial averaging between min and max and use those average ones. And that, of course, the bandwidth averaging 5% is also necessary. And so the LLDD response, as I talked about, can be done in the same kind of way from the simulation. That if you're doing your free field illumination, you can use B-dot probes to measure your surface currents, and then use a transfer function to do that conversion from your test results to a free field response. And then here's samples of different magnetic field probes, or B-dot equivalents, that were placed within our model at the different locations. And so finally, one of the things that always gets brought up is some of the higher frequency applications. And so it's quite easy to understand for the cable response to a HIRF environment how your simulation model can resolve those details. And that up to 400 megahertz, it's very doable within our finite difference simulation approach. Of course, there are other techniques for going to higher frequencies, and they certainly have merit and value in using that, but that's not the approach that we use at EMA. For the finite difference analysis that we do, really with the increase in computational abilities of computers today and the clustering of machines, that we have the ability to sort of sectionalize the aircraft into the different zones. That if you're looking at the cockpit and there's a bulkhead in the back and there's a floor, or you're looking at the base of it, you can resolve that portion of the aircraft with a very fine mesh, and that can get you up to your 18 gigahertz frequency level that you need for aircraft verification. And it's justifiable to use this approach if you have appropriate bulkheads or block-offs to sort of separate those regions from each other in your aircraft. And so we have had very good success in doing these kinds of analysis recently with the, as I mentioned, increase in computational ability that exists today. And so really we can run these results up to the 18 gigahertz necessary for verification purposes. And so of course, there are considerations and different types of models that you can build for this, but really, we think that using this subgrid, submodel approach and these box region probes, and using the average field analysis and 5% bandwidth averaging is very comparable to what is done during testing, and for other reasons I've mentioned throughout this presentation, can expand upon and create more value than what can be done by testing alone. So that's the end of what I have prepared for this webinar. So in summary, HIRF is a specific electromagnetic environment that aircraft must be able to operate safely through. There are guidance documents available that can walk you through the certification steps and give insight as to some of the analysis and processes that must be completed for compliance demonstration. If you are not already familiar with those documents, that is a great place to start to increase your understanding about the HIRF design and certification purposes. The CEM simulations, the ones that I have talked about today, are definitely growing in both the design and certification activities associated with aircraft. It is certainly headed that way, both with the increased computational abilities and the increased abilities of the tools that are available today. It is a necessary part of the design and certification experience, in my opinion. And that the tool that we use for it, the EMA3D Cable, is well suited to support these full aircraft environment definitions, both for the LLSF and LLSC. And as I mentioned before, these models that you would develop for one environment can be used for the other environments as well. And you know, it's of course I'm promoting my tool here, but really this understanding of the environments for electromagnetics, it really does take a simulation tool to be able to do that in a very complex and detailed way. And that the tool that we have been building here has been going on for over 30 years now, that EMA has been building EMA3D, and we've been developing and nurturing and increasing the capabilities of this tool to support our customers and to complete the work that the aircraft companies have to do for the design and certification purposes. So we really are proud of this tool and do use it in our consultation services that we provide. So that's what I have for my webinar today. Thank you all for joining. We'll open it up to some questions now. And if we don't get to your question, I'd be happy to address it by email after the webinar is over. Thank you very much.
All right, thank you, Cody, for that informative webinar. Now let's get to the questions we've received. So the first one we have is from T. Murray. It is, are the post-processing efforts done with the EMA3D tool?
That's a very good question. And so the ability to do the Fourier transform from the time domain to frequency domain is a built-in product of our tool. The 5% bandwidth averaging as of now is not. That's something that we would use either a MATLAB or Python script to do. A lot of the post-processing we do, but we are trying to improve those sort of post-processing capabilities, and that the min and max and averaging is something that we'd like to be able to include as well, because that is, as I mentioned, a very important part of your field specification.
All right, the next question is from James Colati. It is, when modeling the group of STPs, are the shields of the individual STPs isolated from each other, or are the shields in contact?
That's a good question. And so we typically assume that there is a jacket, or that there is a dielectric layer on the outside of those shields, so that when we're modeling them, there is no direct electrical contact. And most typically, when you connect those TSP shields to the bulkhead or the box that you have, you're peeling those shields back and joining them at the connector. So the place that there is electrical connection between those shields is at your bulkhead and box connections.
All right, next question is from Chris Ritter. It is, when simulating LLSC testing, does the tool have the capability to account for the LRU impedance? If not, do you need to add a standard impedance to remove some of the reflective noise?
That's a good question. And so we certainly, when we're considering the terminations associated with our cables, we have different impedances that can be applied to the end. And so that's, if you're talking about, your L, R, or C values that might be associated with your LRU and your circuit terminations, those can be estimated and added. We do not have in these full wave simulations the ability to represent all the details of the LRU, but the front end characteristics are usually good enough for that. But typically, the response on your bundle cables is more driven by your shield properties. If you have bare conductors, so they don't have shields, then what I just said certainly applies, that we can represent those terminations in LRC for your unshielded cables. But for all your shielded cables, the response on your bundle is more driven by your shield properties and the branching associated with those shields. Good question.
All right, the next question is from James Colati. How are the shield terminations modeled? For example, shield to back shell to connector, connector to connector, connector to chassis, chassis to airframe?
Yeah, very good. Yes, it kind of ties in with what I was saying before, that we have in our model, we have terminations that are specified in terms of RLC. And so that if you had a series of terminations from to back shield to connector to a box, that you could put those in a series mode, or you could lump them together. And that there's ways that we can allow the electromagnetic energy to penetrate into the interior of those cables based on those RLC properties. And so really it's a characterization of your transfer impedance associated with your connectors that you need to characterize. That's something that can be measured and implemented or can be estimated. So we don't resolve the fine details in order to do that. We would do an estimation of those properties in terms of RLC and then apply that in the simulation model.
And then we have another one from James. It is, will the view graphs be made available?
Yes, that the presentation will be made available to the attendees of this webinar.
And then we have a comment from Marina. She just says, thank you very much, Cody. So I just wanted to do that.
You're welcome, Marina. Thanks for joining.
And then we have a question from T. Murray. Are the aircraft certification offices in Long Beach or Seattle familiar with EMA3D?
Good question. It depends on who you talk to. So yes, the types of analysis we do and the simulation support we've provided for different aircraft programs has a reputation worldwide. And whether or not specific individuals are aware of it, I don't know the answer to that. But in general, yes, authorities are aware of these 3D analytical tools and capabilities.
All right, and then we have one more question from Edward Barnes. He says, does EMA3D Cable work for lightning indirect effects too, or is it a different software package with the same model?
Good question, Ed. It's the same. And so when I say that you can use the same model for HIRF and indirect effects, it is just a different source application. And so that if in the case of HIRF, we're using a plane wave illumination, a Gaussian pulse with a certain frequency cutoff, what we use for lightning is the exact same model, exact same mesh, same harness configuration, but we would apply a current density source that would mimic a lightning attachment. And then we would use a detached line at, the detached location. And so rather than a plane wave illumination and coupling that way, it's a current excitation that we use for lightning indirect effects.
Okay, and we did just get another question from Chuang. He said, why not use worst case coupling instead of using the average spatial and 5% frequency? Is the worst case more realistic for certification?
That's a very good question. And then so part of this should be addressed in your analysis plan. But sometimes it's no problem for you to use the worst case in the most severe environment that you measure or analyze, and that your system level verification can go forward using those severe levels. Sometimes it's too severe and it creates problems, and then it's more meaningful to use the average values. Part of the point I'm trying to make is that when you do these simulations, you have to validate them to testing. And if you're going to validate to testing, that they use more of that averaged value result from the setup that they have during testing. And that so if you're trying to say that your validation is complete and robust, you may have to use some of those box region averaging to get your results to compare well to the testing. Certainly you can go in and argue that you're capturing a severe response and that can be used for verification. But if you want to increase the confidence in your results when validating to testing, you may have to do some of that averaging.
All right, it is time to conclude this session. As a reminder, any questions that we didn't get to will be addressed by email. You'll also be receiving an email from us with a link to the recording of this presentation. If you have any questions about a particular section, please feel free to reach out through EMA3D.com website or via email. Thank you for your time and attention, and have a great rest of your day.
Thank you.